Good morning, everybody. In today's episode, we're going to be talking about differentiability and continuity and how they're related to each other. First, we're going to look at an alternative form of the derivative that we can use to determine differentiability of a function. So we can say if we know the value of x, c is a constant, that the derivative at x equals c is equal to the limit, and in this case, instead of h going to 0 or change of x going to 0, we're sending x towards c, which brings the points closer together. So now let's look at the fraction part of our derivative. And remember, this is essentially the slope formula, change in y over change in x. So the change in y is f of x minus f of c, and you can see the change in y between the point c f of c and x f of x is f of x minus f of c, and the change in x is x minus c. So let's see what happens when we send the x coordinate to the c coordinate. You can see that as we get closer, our secant line is becoming closer and closer to a tangent line. Okay, so as x and c get closer together, our secant line essentially becomes a tangent line and gives us the exact slope of the curve at x equals c. Okay, next we're going to look at a function f of x equals x to the 2/3 power, and I included a graph of the function here. Interesting function, and our question is, or our task is to find the derivative or the slope at x equals 0. Well, if you look carefully, you might notice that this really doesn't have a slope at x equals 0. The left side is getting infinitely steep as we head towards 0, and the right side, as you back up towards 0, is getting infinitely steep. So from the graph, we can see that this function at x equals 0 is not differentiable. But let's show that using our alternative definition of a derivative. So let's use our alternative definition of a derivative to find f prime of 0. So recall f prime of c, in this case c is 0, is the limit as x approaches c, in this case 0, of f of x, so that's x to the 2/3 minus f of 0. So 0 to the 2/3 is 0. And then the denominator, x minus 0. So what is this? This is x to the 2/3 over x. So the limit as x heads towards 0. And that's 2/3, x to the 2/3 over x to the 3/3. And that's going to give us 1 over x to the 1/3, or x to the negative 1/3. Now this is equal to, as x heads towards 0, it's equal to 1 over 0, which is infinity. Now recall, when we have infinite limits, limits that are infinite, we need to see what kind of infinity we're talking about. This could be negative infinity, this could be positive infinity. So we want to do left and right side limits. So let's take a look at our left and right side limits. So first, the left side limit. So as x heads towards 0 from the left, so these are negative numbers, of 1 over, and this is going to be a negative, 1 over a negative. So that's going to be negative infinity. And if we look at the right side limit, that's the limit as x goes to 0 from the right. Now we've got positive numbers going into x. They're going to be infinitesimally close to 0, so essentially 0, but they're going to be positive. So this is 1 over a positive, something close to 0, and so that's a positive infinity. And if you take a look at the graph, this supports that. The derivative, the slope, because remember these limits are the derivatives, is getting infinitely steep negatively, and then to the right it's starting out infinitely steep positively. So that's where we get the negative infinity and the positive infinity. So in conclusion, in this problem, we would say then that the function is not differentiable at x equals 0. Okay, to summarize the point about left and right-sided limits and their relationship to derivatives, I want to maybe point out the obvious, but since our derivatives are limits, the left-sided derivative is going to be the left-sided limit. So we could even call this the left-sided derivative. Same with the right side. So notice the difference is we're approaching the constant c from the left and from the right. And if the left side limit does not equal the right side limit, or if the left side derivative, which is the same thing, does not equal the right side derivative, then the function is not differentiable at x equals c. In our previous example, we saw limits that were infinite. In this example, our limits will be finite. So let's take a look at the function, the absolute value of x minus 3, and our job is to find its slope at x equals 3. So let's take a look and see how that looks graphically. So you can see at x equals 3, the function has a negative slope leading up to it. So its left side derivative is going to be negative, and its right side derivative is going to be positive. And it switches right at x equals 3. So there's no way that our left-sided derivative and our right-sided derivative can agree. So let's see how that looks when we plug everything into our alternate form of a derivative. So our derivative, f prime of 3, is going to be the limit as x heads to 3 of f of x minus f of 3. So 3 minus 3 is 0. Absolute value of 0 is 0. All over x minus c. In this case, that's 3. So let's simplify that. Now, this looks a lot like x minus 3 over x minus 3, which would be 1, but we do have the issue of the absolute value. So let's bring in some one-side limits to help with our investigation here. So the left-sided limit is going to be the limit as x goes to 3 from the left of the absolute value over x minus 3. Now, if we plug values into x that are less than 3, this is going to be positive, no matter what, because it's the absolute value. But if we put values of x that are less than 3 and then subtract 3, that's going to be negative. So this is going to be a positive over a negative, and so that gives us a negative 1. So the left-sided limit, or the left-sided derivative, is negative 1. Now let's take a look at the right side. So let's look at the right-sided limit. And you'll see, again, that our numerator will always be positive. Absolute value is always positive. But as x gets closer and closer to 3 from the right, our denominator is going to be positive also, because these coming from the right of 3 is coming at 3 from x values that are greater than 3. So this is positive 1. Now, because our left-sided limit and our right-sided limit don't agree, we could write that f of x is not differentiable. It does not have a derivative at x equals 3. Next, I want to talk about the relationship of differentiability and continuity. So I'm going to start with what I think is a simple statement. It should make sense. If a function is not continuous at x equals c, it doesn't exist at x equals c, then the function is not going to be differentiable at x equals c. There's nothing there. It's either an asymptote or a whole, but the function doesn't exist, so you can't differentiate it at that point. So I'm going to take the same statement now, and I'm going to take the contrapositive of that statement. So if the function is not continuous, then the function is not differentiable. So I'm going to say then that if a function is differentiable at x equals c, then the function is continuous at x equals c. So if a function can be differentiated at x equals c, that means it exists and it's continuous at x equals c. Now, what this does not say is that if a function is continuous, then it is differentiable. We have cases that are continuous and not differentiable, and we've seen some examples in today's episode. Here's a graphical look at some of the examples we saw. So the examples that we see here are examples where we have continuity, but we do not have differentiability. Our first example is what we call a cusp. In the case of a cusp, our left and right side derivatives do not equal, but the left side derivative is infinite. In this case, it's a negative infinity at 0. And the right side derivative is positive infinity at 0. So these left and right side derivatives do not equal, so this function has no differentiability at x equals 0. Our next example is a corner. This was the absolute value of x minus 3. Now, similar to cusps, the left-hand side derivative and the right side derivative are not equal, but what is different is that the left side derivative is a constant, in this case negative 1, and the right side derivative is also a constant, and that makes the feature we call a corner. Our final example is the case of a vertical tangent. If we have a vertical tangent at the point that we're finding the derivative, in this case we're looking for the derivative at x equals 0. You can see at x equals 0, the function has a vertical tangent at that point. So if there's a vertical tangent, there is no differentiability, but as you can see, the function is continuous. So those are the three cases that you need to know where we have continuity without differentiability: the cusp, the corner, and the vertical tangent.